Hello everyone, myself Dr. Prianka Sharma, Associate Professor in Department of Physics, School of Basic and Applied Sciences, Maharaja Agrawal University. I am going to discuss about basic properties of nuclei. Before discussing about the basic properties of nuclei, I would like to tell about what is nucleus. As we all know, atom is the smallest part of an element. Atom as a whole is electrically neutral, but it can emit positively or negatively charged particles. Hence, atom is made up of positive and negative charges. Now the point is, how are these positive and negative charges distributed within the atom? So we would first of all discuss about the structure of an atom. First of all, first model of an atom was proposed by J.J. Thomson in 1897. This model was also called plum pudding model. The postulates of Thomson model are: an atom is considered to be a sea of positively charged particles evenly distributed throughout the atom, similar to the red portion of a watermelon. And negatively charged particles are randomly distributed in the sea of positive charges like black seeds of watermelon. Now there are some limitations of Thomson model. Thomson model failed to explain the stability of an atom because it failed to explain how positive charges hold negative charges. It also failed to explain the scattering of alpha particles by thin metal foil. And no experimental support was provided for this Thomson model. To provide experimental evidence to the Thomson model, Rutherford carried out scattering of alpha particles by thin metal foil. He assumed that if Thomson model was accurate, then positively charged alpha particles should be scattered from within metal foil, since atom consists of sea of positive charges. Now Rutherford gave this experimental evidence that when gold foil was taken as a sheet and alpha particles were about to strike this gold foil, it was seen that most of the alpha particles went straight within the gold foil and very few particles were deflected by large angles and very few particles were deflected by small angle. Now the postulates of Rutherford model. All the positive charges and the entire mass number of the atom is concentrated in a very small part of the atom. This central core is called nucleus. The dimensions of the nucleus is negligible compared to the atom. Radius of the atomic nuclei is considered to be 10 raised to power of minus 13 to 10 raised to power of minus 15 meter. And radius of an atom was considered to be 10 raised to power minus 8 meters. Therefore, according to Rutherford model, an atom contains mostly the empty space. Some alpha particle suffers little deflection while passing by an electron. This suggested that outside the nucleus there are electrons that make the atom ultimately neutral. According to Rutherford model, the entire mass of the atom is concentrated in a tiny positively charged portion called nucleus, and negatively charged electrons move around the nucleus. These electrons in the Rutherford model move around the nucleus in different energy levels constantly. When electron moving in circular orbits or energy levels around the nucleus, the Coulombic attraction was balanced by the centrifugal force of attraction. Otherwise, the electrons will fall in the nucleus. Therefore, Rutherford arrangements were quite similar to the solar system model. Now, there are also some limitations of Rutherford model. A moving charged particle always emits radiation with specific wavelengths. Thus, loss of kinetic energy and eventually hit the nucleus of an atom. If the energy of electron loses continuously in the Rutherford model, the observed atomic spectra should be continuous while consisting of broad bands merging in one into the other. To overcome the limitations of Rutherford model, Bohr suggested another model. This model was proposed by Niels Bohr in 1915. This is a modified form of the Rutherford model. Bohr modified this atomic structure model by explaining that electrons move in fixed orbitals called shells and not anywhere in between, and he also explained that each orbit or shell has some fixed energy level. Rutherford basically explained the nucleus of an atom, and Bohr modified that model into electrons and their energy levels. Now, there are some postulates of the Bohr's model of an atom. In an atom, electrons which are negatively charged revolve around the positively charged nucleus in a definite circular path called orbits or shells. Each orbit or shell has fixed energy, and these circular orbits are known as orbital shells. The electrons in an atom move from lower energy level to higher energy level by gaining required energy, and an electron moves from higher energy level to lower energy level by losing energy. Now, these are some limitations of Bohr's model of an atom. Bohr's model of an atom failed to explain the Zeeman effect, which is the effect of magnetic field on the spectra of atoms. It also failed to explain the Stark effect, which is the effect of electric field on the spectra of atoms. It violates the Heisenberg uncertainty principle. It could not explain the spectra obtained from larger atoms. Hence, the present-day atomic structure is the combination of postulates of both Rutherford and Bohr's model. Rutherford explained that whole of the positive charge of an atom is concentrated in a tiny portion called nucleus, which is the core of an atom, and Bohr explained that negatively charged electrons revolve around the nucleus in certain specified orbits called shells. Now, we will discuss about the constituents of an atom. Atom consists of the nucleus. Now, the thing is, which particles exist inside the nucleus and which particles exist outside the nucleus. Various theories were given. Someone suggested that proton-electron resides inside the nucleus. Now, the proton-electron theory says that electron cannot exist inside the nucleus. Now, contradictions with this is, first is the spin consideration. When we consider the spin of electrons and protons, both of the particles have half spin. Hence, nucleus must have integral spin if it contains an even number of proton and electron, and half integral spin if it contains odd number of proton and electron. But experiments show that spin depends on mass number A. Spin of nucleus is 0 or integral for even A and half integral for odd A. This contradicts the assumption of electron to stay within the nucleus. Also, according to uncertainty principle, if electron stays inside the nucleus, then position of the nucleus is definite. That is, within the nucleus radius 10 raised to power of minus 14 meters. Hence, we define the position of the nucleus. Then from uncertainty principle, electron should come out of the nucleus with energy of 200 MeV, which is quite high. Experimentally, it has been found that electron comes out of the atom with energy of just 2 to 3 MeV. So, if we define the energy of the nucleus to be 2 to 3 MeV, then position of the electron comes out of the order of 10 raised to the power of minus 8 meter, which is dimensions of an atom. Thus, it was concluded that electron does not reside inside the nucleus and only proton reside inside the nucleus. To overcome the considerations of spin, it was considered that along with proton, neutrons stay inside the nucleus. Neutrons are neutral particles and they have the same spin as protons. Now the nuclear size was given to be 10 raised to the power of minus 14 to 10 raised to the power of minus 15 meter. Nucleus radius was given to be r is equal to r naught a raised to power 1 by 3, where r naught varies slightly from one nucleus to another but is roughly constant for a greater than 20. Present experimental evidence shows that R naught is equal to 1.2 plus minus 0.1 into 10 raised to the minus 13 centimeter, and variation in R naught is from 1.2 to 1.5 Fermi. Thus, volume of nucleus is directly proportional to the total number of nucleons. This suggests that all nuclei have nearly the same density. Nucleons combine to form a nucleus as they were tightly packed spheres. So volume is 4 by 3 pi r cube with r is equal to r naught a raised to power 1 by 3. So nuclear density rho comes out to be mass over 4.3 pi r naught cube. Now we will discuss about a term mass defect. We all know that nucleus consists of protons and neutrons. It is predicted that mass of a nucleus should be equal to sum of the individual masses of the constituent neutrons and protons. However, it is observed experimentally that actual mass is less than sum of individual masses of the constituent neutrons and protons because nucleons are tightly packed within the nucleus. Thus, mass defect denoted by delta M is defined as difference between sum of the masses of constituent nucleons, that is protons and neutrons, and total mass of nucleus. If Mn is mass of neutron, Mp is mass of proton, Mza is mass of bounded nucleus, then mass defect delta M is given by Z dot Mp plus A minus Z dot Mn minus Mza. This mass defect is in form of energy and is responsible for binding the nucleons together. Then we will discuss another term, packing fraction. It is observed that atomic masses are close to whole numbers, but they invariably differ from integers by small amount. This deviation of atomic mass from whole number is expressed in form of a quantity called packing fraction. This packing fraction F is defined as mass defect per nucleon. It is denoted by small f is equal to delta M upon A. From the graph we see that packing fraction measures the comparative stability of the nucleus. Smaller the packing fraction, larger is the stability of the nucleus. Lighter nuclei like hydrogen, helium, carbon do not fall on this curve. Therefore, these are stable atoms. Packing fraction beyond mass number 200 becomes positive and increases with increase in mass number. Another term we will discuss is the binding energy. The nucleons are bound together in a nucleus and the energy has to be supplied in order to break apart the constituents into free nucleons. The energy with which nucleons are bounded together in a nucleus is called as binding energy. Binding energy is defined as energy required to free nucleons from a bounded nucleus. It is given by delta M dot C square. The binding energy per nucleon is maximum when packing fraction F is minimum, since for the nuclei from A greater than 20 to A less than 200, packing fraction F is negative. Hence, the binding energy per nucleon for these nuclei is more. Higher the binding energy per nucleon, more stable is the nuclei. From the graph, it is clear that except for the nuclei helium-4, beryllium-8, carbon-12, oxygen-16 and neon-20, binding energy curve for all other nuclei is generally continuous and linear. The binding energy per nucleon of some light nuclei such as hydrogen-1, hydrogen-2 and hydrogen-3 is very low. But for all other nuclei, binding energy per nucleon is nearly 8 MeV. The binding energy per nucleon is positive for all values of mass number A. It means that all the nuclei are stable. For heavier nuclei, the binding energy per nucleon changes very irregularly from one nuclei to other nuclei, and its value for the nuclei helium, beryllium, carbon, oxygen, neon is more as compared to that for the other nearby nuclei. That is, for these nuclei, there are peaks obtained in the binding energy curve. For the nuclei of mass number A greater than 20, the binding energy per nucleon is nearly constant, 8.04 MeV. It concludes that inside the nucleus, the nucleons exert forces on the other neighboring nucleons only in a limited number. That is, the nuclear forces are saturated. Near the mass number A is equal to 56, the binding energy per nucleon is maximum, nearly 8.8 MeV. And then it gradually decreases with increase in mass number A. And ultimately, for the heavy nuclei of mass number A greater than 200, such as uranium, etc., its value becomes nearly 7.6 MeV. It shows that nuclei near the mass number A is equal to 56 are relatively more stable, and the nuclei of mass number A greater than 200 are relatively less stable. That is, they are radioactive. Nucleus spin. A nucleus is made up of protons and neutrons which move inside the nucleus as electrons revolve around the nucleus. These nucleons revolve as well as rotate on their axis. Since any rotating object possesses a property known as angular momentum, hence nucleons possesses both orbital angular momentum L due to orbital motion in the nucleus and intrinsic spin angular momentum S equal to 1 by 2h per nucleon due to its rotation on its own axis. This total angular momentum of a nucleus is called nucleus spin. Nuclei have low spin in their ground state as compared to spin in the excited states. Spin of the excited state differ from spin of the ground state by integral multiple h. All even nuclei have spin 0. All odd nuclei have integral spin. All odd even nuclei have half integral spin 1 by 2h. Electric quadrupole moment. We have assumed that nucleons inside the nucleus are so distributed that spherical symmetry is maintained in them. That is, shape of the nucleus is spherical ideally. But actually the shape of nucleus is not spherical, but it is elliptical. In other words, the elliptical shape arises due to non-uniform distribution of the electric charge within the nucleus, or quadrupole moment measures the extent of deviation of nuclear shape from spherical symmetry. Electric quadrupole moment is given by Q is equal to 1 upon E integral 3z square minus r square rho dV. If the positive charge of nucleus is distributed perfectly, then the nucleus is spherical in shape. But if the charge distribution inside the nucleus is elliptical with major axis along the spin axis, then Q is positive, known as prolate shape. If charge distribution inside the nucleus is elliptical with minor axis along the spin axis, then Q is negative, known as the oblate shape. The concept of statistics is also related to the behavior of large number of particles. There are two types of statistics: FD statistics known as Fermi Dirac statistics and BE statistics known as Bose-Einstein statistics. FD statistics apply to a system of particles for which wave function is antisymmetrical. That is, wave function changes sign with interchange of coordinates. Pauli's exclusion principle applies, that is, no two particles can occupy their same quantum state. Electrons, protons and neutrons which have spin half integral are all fermions and obey FD statistics. All odd A nuclei obey FD statistics. Bose-Einstein statistics apply to a system of particles for which wave function is symmetrical, that is, wave function does not change sign with interchange of coordinates. Two or more particles can be in the same quantum state. Photons, deuterons, etc. are called bosons having zero or integral spin. All even A nuclei obey the Bose-Einstein statistics. Nuclear forces. Density of nucleus is very high, of the order of 10 raised to the power of 17 kg per meter cube, and independent of A. All nuclei have almost same density. Density is not uniform throughout a given nucleus but varies. Its maximum at the center and falls off with distance. Nucleons are closely packed in the nucleus. Due to positive charge on protons, there exists Coulomb's repulsion between protons, which will try to fly away from the nucleus. But the fact that nucleus is stable implies that net forces between proton-proton, neutron-neutron, proton-neutron pairs must be attractive. Moreover, these attractive forces must be stronger than the Coulomb's repulsive force between large number of protons in heavy nuclei. This attractive force which binds the nucleons together is called nuclear force. Nuclear force is strongest force in nature. Properties of nuclear force. They are attractive in nature. They are strongest known forces. They are short range forces. They are non-central forces because they can't be represented along the straight line joining the center of two intersecting nucleons. They are charge independence, that is, force is same for proton-proton, neutron-neutron, proton-neutron. They are spin dependent. They are basically exchange forces. They are saturated forces, that is, a nucleon interacts with only limited number of nucleons and not all the nucleons present inside the given nucleus. I have used the term here exchange forces. Now, exchange forces can also be known as meson forces. Basically, it is said that nucleons, that is protons and neutrons, are further made up of mesons. These mesons form pulsating a cloud around some core inside the nucleons. These mesons are supposed to rapidly jump back and forth between the nucleons, thereby changing their identity equally fast at the same time, keeping them bound together. Now I will discuss about some models. Liquid drop model. Liquid drop model describes atomic nuclei in which the nucleons, that is neutrons and protons, behave like molecules in a drop of liquid. If given sufficient extra energy, the spherical nucleus may be distorted into a dumbbell shape and then split at the neck into two nearly equal fragments, releasing energy. Although inadequate to explain all nuclear phenomena, theory underlying the model provides excellent estimates of average properties of nuclei. As the nuclear molecules in a liquid are held together by van der Waals forces, that is only between near neighbors, similarly nucleons in a nucleus are held together by strong nuclear force, which is a short range force that appears to act only between neighboring nucleons. A nuclei is generally taken to be spherical with radius r is equal to r0 1 upon 3. On the basis of this concept, some other classical concepts such as surface tension, electrostatic repulsion, etc., a formula for the atomic mass of a nuclide in terms of binding energy corrections terms was set up by Wiesecker in 1935, which was later on modified by Bethe and others. This formula is known as semi-empirical mass formula, was then used to predict the stability of nuclei against particle emission, energy release and stability for the fission. The advantages of the liquid drop model is that the model is useful in predicting the masses of nuclei that are far from stability, where masses are hard to measure. Many refinements beyond that we have done and we have been added to the model to improve accuracy. But this liquid drop model has several shortcomings also. It is not quantum mechanical. It assumes that nuclei are spherically symmetric, which disagrees with the fact that nuclei have non-zero quadrupole moments, and nevertheless the model does not help us understand the nuclear stability. The binding energies predicted by the liquid drop model underestimate the actual binding energies of the stable nuclei, for which either the number of neutrons or the number of protons is equal to the following numbers: 2, 8, 20, 28, 50, 82, 126. These are called magic numbers because nuclei having number of nucleons satisfying these numbers show unusual properties other than nuclei. The modification of liquid drop model was given by shell model. These magic numbers can be explained in terms of shell model of the nucleus. According to shell model, each nucleon in a nucleus moves under influence of some potential and classifies the energy levels in terms of quantum numbers n, l, j in the same way as the wave functions of the individual electrons classified in atomic physics. Energy levels come in bunches called shells with large energy gap just above each shell. The energy eigenvalues depend on principal quantum number n and the orbital quantum number l, but are degenerate in the magnetic quantum number m. This is the energy level diagram for the shell model. First we see that this 2, 8, 20, 28, 50, these are the magic numbers and shell closures occur at these magic numbers. We have S, P, D, F shells and these are filled accordingly. The spin orbit couplings. Spin orbit coupling is interaction between orbital angular momentum and spin angular momentum. Each nucleon in the nucleus experiences a strong inverted spin orbit interaction in addition to the net nuclear potential. Because of the strong coupling, the two vectors L and S combine to form total angular momentum J for the particle. So J is equal to L plus S, where S is equal to plus 1 by 2 or S is equal to minus 1 by 2. So therefore the total angular momentum J can be either L plus 1 by 2 or L minus 1 by 2. Hence, these are two possible ways of combining S with L, giving rise to two different levels. The spin orbit interaction splits each of the highest particle level in two levels, one with higher energy level L minus 1 by 2 and other with lower energy level L plus 1 by 2. Splitting increases with L and can become so large that for a given L, J is equal to L plus 1 by 2, level slides down to energies as low as those of the multiplet with quantum number n minus 1. I hope we have discussed some of the properties of the nuclei. Thank you.